All right, let's go over some questions from quiz 8. All right, let's start with this question. What is true of these two molecules? Okay, we see that we have a higher boiling temperature for substance A, and therefore we have stronger intermolecular forces in substance A. Therefore, at any given temperature, you should have a lower vapor pressure, because if the intermolecular forces are stronger, the molecules are held tightly in the liquid phase. Therefore, it is harder for them to go to the gas phase by disturbing or breaking these intermolecular forces. Okay, so that's why the two vapor pressure curve 2 should go with A, and therefore B should go with 1. Okay, now let's look at the options. B corresponds to vapor pressure curve 2 is incorrect. A corresponds to vapor pressure curve 1 is also incorrect. A corresponds to vapor pressure curve 2, that's right, because it is more polarizable. That is perfect. Yes, sulfur, when we have sulfur, we have more electrons, therefore it should be more polarizable. So that is correct. B corresponds to vapor pressure curve 1 because it has stronger interactions. No, vapor pressure curve 1 has a higher vapor pressure at any given temperature, meaning it has overall weaker intermolecular forces. So that is incorrect. So the correct answer must be option 3. Okay. So no, this one, option 3. Moving on to next page. Which option correctly ranks the molecules based on the strength of their dipole-dipole forces? Okay, just remind us about dipole-dipole interactions. Dipole-dipole forces, I want a different color, by the way. Give me a second. Let's have blue. Okay, dipole forces strength depends on the molecular polarity or the net dipole moment. Net dipole moment. Okay, so the molecule with the greatest net dipole moment or greatest net polarity or molecular polarity will have the strongest dipole-dipole forces. Out of these substances, HF, these are linear molecules, HF has the greatest electronegativity difference because hydrogen is 2.1, fluorine is 4.0. Therefore, it has the greatest net dipole moment, and as a result of that, it will have the strongest dipole-dipole interactions. So therefore, options A and C are out. And between options B and D, we need to consider HCl versus HBr. So when you go down the group, so fluorine, chlorine, bromine are in the same group. When you go down the group, the electronegativity decreases. Okay, so that means the electronegativity difference between, say, HCl and HBr. Okay, I think chlorine is 3.0, hydrogen is 2.1, hydrogen 2.1, and bromine is around 2.4 or something. Okay, so we have the least electronegativity difference in the HBr bond, meaning it is the least polar bond. So because it is a one bond molecule, the bond polarity is the molecular polarity. Therefore, HBr is the least polar molecule, which will result in the weakest dipole-dipole forces. So that answer is option B. Okay, so let's select that. Moving on. Question 3. What types of intermolecular forces can this molecule have with molecules of the same type? Okay, so again, this molecule has nitrogen over here and then hydrogen bound over here. Okay, immediately my focus goes to that part of the molecule because rest of the molecule is consisting of carbon and hydrogen, which is non-polar for all intents and purposes. But because of the presence of this nitrogen atom here, this molecule is going to have a partial negative charge around the nitrogen atom. compared to the rest of the molecule. Therefore, this molecule is polar. So you know that any molecule, whether it is polar or non-polar, will have dispersion forces because all the molecules have electron cloud that can be perturbed to make it polarized. That's what it's meant by polarizable, and that gives rise to opposite partial charges that can be interacted, that can have attractive interactions with each other. Right? So dispersion forces are there in all molecules, whether it is polar or non-polar. And then this molecule is a polar molecule. Let me do something over here. So if I draw the net dipole moment, it should go towards go towards nitrogen, something like this. Okay. Because it has a net dipole moment, it has dipole-dipole forces as well, because its net dipole moments can interact head to tail. Head is partially negative, tail is partially positive. They are attracted to each other. Therefore, we have dipole-dipole interactions. And on top of that, we have hydrogen bound to nitrogen. Okay, we know when we have hydrogen covalently bonded to either nitrogen, oxygen, or fluorine, these molecules can engage in hydrogen bonding forces as well. So it has all three types of intermolecular forces. The correct answer is option 4. Okay, so select that. Moving on. The normal boiling points of these molecules are given respectively. Select, these two substances have the same number of electrons. Okay. Which of the following options best explains the difference in boiling points? Okay, so that is great that we are already told that they have the same number of electrons. If that is the case, they are going to be equally polarizable, more or less, and therefore equally polarizable based on the number of electrons. But however, when it comes to C3H6, okay, it's going to be a larger molecule because CF4 looks like this. This is CF4. Okay, and CH3 is going to be spread out in a larger space. Okay, so here's C3H6. Okay, I think what we have here is not this, something like this. Yeah, so this is C3H6. So it is spread out in a larger space, and as a result of that, because the same number of electrons are in a larger volume in C3H6, we can expect that to have a higher, stronger intermolecular forces, stronger dispersion forces. Okay, and as a result of that, that will have a the higher boiling point. So that's why we have a higher boiling point for C3H6 compared to CF4. Okay. Now again, remember both of these molecules are non-polar molecules. This is non-polar because of their symmetry, symmetric distribution of charges. The CF4 is non-polar, and then this is considered non-polar because that only contains carbon and hydrogen. Okay, even though they have the same number of electrons, because you have a larger volume in this molecule over here, it's going to be more polarizable. Therefore, it's going to have stronger dispersion forces. Let's see what we have here. C3H6 can engage in hydrogen bonding forces. That is incorrect because we don't have hydrogen covalently bonded to either nitrogen, oxygen, or fluorine. CF4 is less polarizable as it is non-polar. Yeah, we'll table this for the moment. We'll come back to it. C3H6 is more polar. No, that is incorrect. Both of them are non-polar. CF4 is less polarizable as it has a smaller surface area of contact. So between these two, I would go with actually. So if it has a less surface area of contact, Okay, that means, I mean, the molecules are gonna get less polarizable, because to get polarized, you need another molecule coming closer to it. If you have a lesser surface area of contact, that means it has a barrier. The other molecules have a barrier to get closer to it, and therefore it's going to be less polarizable. So that is not bad either. So I'm going to go with this answer over here, the less surface area of contact, or smaller volume. Okay. Okay. And then what I don't like about option B is it is less polarizable as it is non-polar. Now, being non-polar and polarized, and the polarizability does not have any connection. Okay, whether it is polar or non-polar. Okay, but the polarizability depends on the number of electrons it has, and then the volume of in the space those electrons are distributed in. So therefore, option B is absolutely incorrect, because I mean, I would not connect these two because they are not related. Okay, therefore the correct answer is option 4. All right, let's go with that. All right, which of the following best represents dipole-dipole forces between these two molecules? All right, again, dipole-dipole always arrange from head to tail. And okay, the other thing is the net dipole moment should be correct. So now we see that we have the net dipole moments correctly drawn in option A. Okay, option B is incorrect because it is showing the bond dipole. It's trying to show the bond dipole moment of the carbon oxygen bond, but that is also incorrect because arrowhead should be facing oxygen, because oxygen is more electronegative, and that is going to get the partial negative charge. Arrowhead is always have a partial negative charge. Therefore, this is incorrect. And option C is incorrect because you see that the partial the arrow tails are interacting, are closer to each other. Arrow tails have partial positive charge, okay, and the same charges repel each other. Therefore, option C is incorrect. And then option D is also incorrect because you see that it is not even showing interactions. And then here the arrowhead is partially negative, and they are closer to each other rather than head being closer to tail. For that reason, option D is also incorrect. The correct answer must be the first option. So I'm going to select that. All right, moving on. Question 6. A molecule has a strongly polar XY bond, and the partial charge on X atom is positive. Okay, so here's the XY bond. We are told that X atom is partially positive, therefore Y atom must be partially negative. Okay, and this tells me that Y is more electronegative immediately. Okay, therefore the bonding electrons will spend more time around the Y atom. That's what gives the partial negative charge there. Okay, and then why does bonding electrons spend more time around the Y atom? Because the Y atom should have a higher attraction or greater attractive interaction towards these electrons. Okay, if we have a greater attractive interactions, we know that it should have a lower potential energy. Okay, anyway, so those are comparing X and Y atoms. Now looking at the answers, electrons in the valence shell in Y have a lower potential energy than electrons in the valence shell in X. I like that. Okay, what this tells is Y atoms have a greater attractive interaction or greater attraction towards the electrons or the bonding electrons, which is related to the valence electrons. Okay, that's why these bonding electrons are going to spend more time around Y, because you have a greater attractive interaction, and that's why the Y is going to get the partial negative charge. So okay, so here what I asked you to do was to connect these attractive interactions we already know based on the electronegativity to the potential energy, because you know the stronger, I should write this because this is the mantra we talked about all the time. The stronger the attractive interactions, the lower the potential energy. Okay, that's the mantra here. Why one is correct. All right. Second point, the element X is more electronegative than Y. No, that is incorrect. If it is more electronegative, then it should get the partial negative charge. But you are told that X is getting the partial positive charge. That means it is less electronegative. Option 3, the bonding electrons will spend more time around Y atom. Absolutely. Okay. So Y is partially negative, meaning the bonding electrons spend more time around the Y atom. Okay, so that is correct as well. So the correct answer must be 1 and 3, which is option 4. Okay. Oh, we have another question over here. No, it's a 3 question. Okay. So let's try the 7th question. Okay. Which of these would you predict to have higher boiling temperature and why? Okay. Now, what we have in one is we have 1, 2, 3, 4 carbons. That is 4 times 6 electrons, and 2 oxygens, 2 times 8 electrons, and hydrogens we have. Okay, I'm counting the electrons, which is a good practice when we deal with this. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, of which should be 8. Okay, this should be 24 plus 16 is 48 electrons. Okay, and then on the other hand, we have in molecule 2, we have 1, 2, 3, 4, 5, 6, 7 carbons. So 7 times 6 plus hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 16. Right, 16 hydrogens, so 16 electrons from them. 7 times 6 is 42. 42 plus 16 is 58. Okay, we have 58 electrons. Okay, now here's the thing. Okay, you have 10 more electrons in molecule 2 compared to 1. Yes, it will have stronger dispersion forces because of that. But here's the thing. On top of dispersion forces, molecule 1 is going to have a dipole moment. Therefore, it's going to have, on top of dispersion, it will have dipole as well. On top of that, it has hydrogen covalently bonded to oxygen. Therefore, it will have hydrogen bonding as well. So you have all 3 types of intermolecular forces, and having 10 electrons more in molecule 2 is not enough to outweigh this hydrogen bonding forces and dipole-dipole interactions in molecule 1. Therefore, we can expect molecule 1 to have a higher boiling point or higher intermolecular forces than stronger intermolecular forces than molecule 2. Okay, 1 because it has hydrogen bonding interactions, dipole-dipole, and dispersion forces. That is true. 2 because no, it's not polar. 2 because its dispersion forces are stronger than intermolecular forces in 1. No, here's the thing. Its dispersion forces are stronger than not all the intermolecular forces. Okay, the dispersion forces are stronger in 2 compared to the dispersion forces of 1. Okay, that would have been a correct statement, but here overall intermolecular forces are stronger in 1. 1, it has more electrons than 2. That is not correct. Okay, yes, it has actually less electrons than 2. That's why it's incorrect. So the correct answer is option A. Okay, so let's select that, and then moving on to the last question. In comparing molecules A and B, which one of them would you predict to have a higher boiling temperature, and what is the most important reason why? Okay, so I definitely, just by looking at it, we know that both molecules have dispersion forces. Okay, both have dispersion, and then in A, on dispersion forces will be a little bit stronger in A compared to B. Okay, but a little bit stronger because it has 7 more electrons, because our hydrogen here is replaced by uh, an oxygen over here, right? So that means it has, so which has 8 electrons. So that means it has 7 more electrons. Therefore, dispersion forces will be stronger. But that is not the main reason. On top of that, you see that this is a polar molecule. Here's the net dipole moment of this molecule. Because you have a net dipole moment, on top of dispersion, we have dipole-dipole, which is usually stronger than dispersion. For that reason, I would expect A to have stronger overall intermolecular forces, meaning higher boiling point, higher density, higher viscosity, higher melting point, and lower volatility and lower vapor pressures and so forth. Okay, so option A is incorrect. They would have the same boiling temperature. No, definitely not. B would have a higher boiling temperature. No. B would have a higher boiling temperature. No. You see that I'm not even reading the rest of the sentence because it is already incorrect. A would have a higher boiling temperature because A has a dipole moment. That's perfect. And A would have a higher boiling temperature because A has more electrons. That is technically correct. A has more electrons than, if I'm not missing anything, yeah, A has more electrons than B. But that is not the main reason why it has stronger dispersion forces. Okay, stronger overall intermolecular forces. The main reason is this. This is much better explanation as to why A should have stronger intermolecular forces than last option. So I'm going to select that one. Okay, this one, and then that's it. Let's see how we did over here, and I'm going to submit the quiz. There you go. That's how we get 100% for that quiz. All right. I think we're going to stop here. Bye, everybody. I'll see you in class.